Our last video discussed the 3 row operations we can use to solve linear systems. Sometimes that process can be written in a more efficient manner using matrices. So a matrix is nothing more than a rectangle of numbers. And they can be used to represent systems. Let's do some examples. So let's suppose I have the system x plus y is equal to 2 and x minus y is equal to 0. A pretty easy system to solve. If I were going to use the row operations to solve it, there's no point in writing down x and y and this equal sign a bunch of times over and over again. That gets repetitive. So we're going to represent this with the important information. The important information is what's in front of the x, y, and what number here is on the right side of the equation. So I'm going to write this as 1, 1, 2 to denote that I have 1x, 1y, and that should equal 2. Sometimes I like to write a little line here to represent that the 2 is on the right side of the equation, but that's optional. The bottom row is 1, negative 1, 0. And then from here, you could do the 3 row operations attempting to get a triangular system. So I'm going to do row 2 minus row 1. I want to get this 1 to be a 0, thereby eliminating the x variable. So this becomes 1, 1, 2. The first row stays the same. I'm changing row 2. 0, negative 2, negative 2. And I think I would like to do negative 1/2 row 2 to finish things up. I will get 1, 1, 2, 0, 1, 1. This is the so-called triangular system I was going for. I have a triangle of numbers and then zeros to the bottom left of the triangle. This is a nice system because I could read off the answer. I can look at the bottom row, and that bottom row retranslates into 0x plus y is equal to 1. So I get y is equal to 1 from the bottom row. Once I know y equals 1, I can plug that into this row, which says x plus y equals 2, and so x also equals 1. Let's do another example of representing a system as a matrix and then using the row operations to understand the solutions of that system. How about if I have x plus y equals 1, y plus z equals 1, and x minus z is equal to 0. So writing as a matrix, I have a column containing the x's, a column containing the y's, a column containing the z's, and a column containing what everything's equal to. The first row is 1x plus 1y plus 0z is equal to 1. The next row is 0 x's, 1, 1, 1, and then 1, 0, negative 1, 0. So I could do row operations. Let's try it. So I could do row 3 minus row 1. The reason I picked that is because I'd like a triangular system. I'd like this entry here to be 0. So I'm going to start there and subtract off row 1, keeping row 1 the same, keeping row 2 the same, but changing row 3 to 0, negative 1, negative 1, negative 1. Next, I want to get rid of this negative 1, again trying to make a triangle. So doing the row operation, row 3 plus row 2 gives 1, 1, 0, 1, 0, 1, 1, 1, and then the last row happens to be all zeros. That's the equation 0 equals 0. And when you get 0 equals 0, that's the situation when you have overlapping lines in your system. This means we have a situation with many solutions. I cannot find a unique solution for x, y, and z, but there's a whole parameterized family. That just means there's a lot of solutions to this equation. We can write down what they are in the following way. Since I have 3 equations I can't find a unique solution. In that situation, I will say, let Z be any number. Once I pin down what Z has to be, I could write X and Y in terms of Z. You can look at the second equation and say, well, if Z is anything, then I can say Y is equal to 1 minus Z. And then looking at the top equation, X is equal to 1 minus Y, which would just be Z. So all solutions are, well, the first coordinate X can be Z, the second coordinate Y can be 1 minus Z, and the third coordinate Z again. Okay, let's finish this video with one final example of using matrix notation. I could have, you know what? Why write down the system to begin with? Why not just start by writing down the matrix? 1, 1, negative 2, 1. So that's the equation x plus y minus 2z is equal to 1. So I'm communicating the same information but in a more efficient manner using matrices. I could have 1, let's say, minus 1, 1, and 0, and 2, 0, negative 1, 4. So I could do a few row operations. The most common row operation is to add a multiple of one row to the other. So I could do row 3 minus 2 row 1. The reason why I chose that row operation is, again, I'm aiming for a triangular system. I'd like to make that 2 I've just circled a 0. And so I can identify the move that gets rid of that 2. Using this row operation, I get 1, 1, negative 2, 1, 1, negative 1, 1, 0, and then the bottom row, let's see, it'll become 0 as required, negative 2, 3, 2. Okay. I'd also like to get rid of this one. My main strategy when doing these row operations on matrices is to start in this bottom entry of the first row and work my way up, putting zeros underneath this first one and then moving to the second row and repeating. So I'm going to aim to make that 1 a 0. The row operation that does that is row 2 minus row 1. If I employ that row operation, the first row stays the same. The second row becomes 0, negative 2, 3, negative 1, and then I think I have 0, negative 2, 3, 2. So I've successfully put a 1 and then zeros underneath that 1 in the first column. The second column, I'm going to try to do the same thing. I'd like to get rid of this negative 2 and put a 0 there. So the row operation I can employ is row 3 minus row 2. This gives me 1, 1, negative 2, 1, and 0, negative 2, 3, negative 1. And the last row becomes 0, 0, 0, 3. Uh-oh. This says no solution. There's no solution because this is equivalent to the equation 0 is equal to 3, which is nonsense. So here's an example of how to represent systems with matrices, and on this page I have the 3 different things that can happen. You might get a unique solution, you might get many solutions, or you might get no solution. Okay, great.